Hello, in this video I'm going to run through the key points of Newton's laws of motion. So this is the foundational topic in dynamics and actually in the whole of classical mechanics. This is completely revolutionary at the time and foundational ever since description of how objects move and the causes of their changes in motion. That's the key part of all of this. We're looking at how forces change motion. I'll give more historical background to Newton's laws in a separate video, but for here, it's useful to know that this wasn't all just Newton's own work. He wasn't working completely independently, making observations and then publishing these laws. It was a long process pulling all this together, and he was pulling together ideas that other scientists had come up with, people like Galileo, Kepler, Hooke of Hooke's law fame. So their ideas and observations and the sort of questions that were still hanging in the air of how to turn all of this scientific work that had been going on for the previous century or so, how to turn all of that into one unified theory. And this is what Newton managed to succeed in doing when he published his Principia Mathematica, one of the most important scientific texts in the history of science. He published this in 1687 after a long time working on this. And it was completely revolutionary. And since then, it's been the foundational document for classical mechanics. So what are Newton's laws of motion? Well, there's 3 laws, and if you opened up 10 different textbooks, you'd get probably 10 different wordings for each one of these laws. So we're not looking at precise wordings here. What we're looking at is the key points, the key descriptions in each law. So starting with the first law, which is our law of inertia. This tells us that the velocity of an object changes only if it's acted upon by a net force. So this has got 2 key points inside it. You've got the idea that it's only forces that change velocity. There's nothing else. If the velocity of an object has changed, that means it's been acted upon by a net force. And then you've got this idea of inertia, which is the resistance to changes in motion. So an object with high inertia, it's very hard to get it to change its motion. Usually this is going to mean something which has got a lot of mass. If you think of a very massive object that's just sitting there, it's hard to get it to start moving. So we've got this idea of inertia as resistance to changes in motion. And this then comes into the second law, which is probably the most used and famous of the 3 laws. This gives us our relationship between force and momentum, because it tells us that the force, the net force applied to an object, is equal to the rate of change of momentum of that object. So we've already described momentum as being the quantity of motion. So a force is saying it's telling us how the quantity of motion is going to change with time. So if we've got a very high force, we're going to get a very high rate of change of momentum. We're going to be building up that quantity of motion. And this fits in with this idea of inertia, because of course the momentum being the mass times the velocity. So if you've got a very large mass, then if our momentum has changed by a certain amount, this huge multiplier of mass means that we're going to have a small change in the velocity. So we've got this built into this relationship between force and momentum, the idea of inertia. This second law is more commonly written in its simplified special case form of F equals ma. The force is equal to the mass times the acceleration, because in the case of constant mass, then this rate of change of momentum becomes the rate of change of mass times the velocity. So if mass is constant, then this turns into m dv dt, which is the mass times the acceleration. But this is only applicable if we've got a constant mass. So it is a special case, and we need to keep that in mind because we're going to start having problems with applying this version of the second law when we move into modern physics and objects moving at extremely high velocities. Then we start getting a problem with this approximation. Right, the third law is essentially a statement of conservation of momentum. And it's saying that if one object exerts a force upon a second object, then that second object will exert a force of equal magnitude and opposite direction on the first object. So just to draw that out in a little diagram, if we got two objects and the first object is sort of pulling the second one towards it with some force F, then the second object will also be pulling the first one towards it with the same force, equal magnitude, opposite directions. And we need this because of the second law and our conservation of momentum. So if we've got a change in momentum, you think if we just look at this second object here, which has got the force pulling it towards the first one, so we're going to get a change in momentum off to the left. Well, if this is a closed system, the total amount of momentum must be conserved. So for the momentum to be conserved, this first object is going to have to move with the same change in momentum off to the right in order to keep the total momentum constant. So the third law is a direct description, really, is a direct consequence of the conservation of momentum. So all in all with these, the most important one that we're going to find in our applications and our path through dynamics is definitely the second law, because that's the one that we're applying in order to solve problems. We're going to be using F equals ma time and time and time again. But you do want to remember the subtleties of the other two laws. You want to remember the idea of inertia. You want to remember that it's only forces that change motion when we're working inside classical mechanics. And you want to remember the conservation of momentum that's intrinsic to the third law. So we want to keep all of that in mind. And while we're applying the second law and using this F equals ma, we don't want to lose sight of the actual full definition of this law, which is that the force is equal to the rate of change of momentum. So we need to keep all of that in mind while we're going through and not lose sight of the bigger picture. Just as one final point, this does come back as well to our definitions of mass. You know, we were discussing this in an earlier video, that mass is a very difficult thing to define. And we were coming down to an operational description of saying, well, the mass of an object is whatever our scales are telling us when we put the object on the scales. But we've now got another possible definition here of mass, this idea of inertial mass, because it's built into Newton's laws here, where we've got that the force applied to an object is equal to the rate of change of momentum. We can look at how objects react to forces that are being applied to them, and that can tell us what the mass is, because we can measure the force F, we can measure the velocity v, and then that will allow us to work out what the mass is through how the velocity is changing with the applied force. So it does give us another way of defining mass. We can say, okay, well, the inertial mass of the object, so we're calling it inertial mass because it's the mass that's built into this inertial relationship between force and motion. And we could work that out and say, right, well, that's a way of quantifying it. We can say that this object is more massive than this other one because it's got a correspondingly smaller change in velocity when we apply the same force. So this m here in the momentum equation, we can say is the inertial mass of an object. So it does give us another option, and we're going to see yet more options coming up in future with these different ways that mass feed into these equations in dynamics. So yeah, that's a brief overview anyway of what's going on with Newton's laws. And like I say, just come back to Newton's laws every now and again, you know, and just refresh your memory on what the key points are. You know, it's great to be able to apply F equals ma consistently and accurately when solving problems, but keep revisiting the laws to make sure that you understand them properly and you haven't just got now this shorthand, oh yeah, Newton's laws is just F equals ma, and you've forgotten everything else, because then you're losing the depth of your description. So keep revisiting all of this.